Okay, so this is pretty amazing. We've got a function here, f of x equals e to the x. And do you remember what e is? It's that special number, Euler's number, which is 2.71828 ... It's an irrational number. And in a previous unit, I explained what Euler's number is and why it is 2.71828 ... Okay, so when I graph that function, there it is there, and you can see that I've got my blue tangent line here, and I've got a point A here that sort of moves through. So here A is equal to 1, and then we've got a particular gradient value at 1. Here is A equal to 2, and we've got a particular gradient at A equals 2. Now the point here is e squared, right? Because a is equal to 2, so it'll be e to the power of 2. So it'll be 2.71828 ... squared. And when a equals 1, that would be 2.71828 ... to the power of 1, which is itself. And when a equals 0, we've got 1, of course. When a equals negative 0.7, we've got 2.71828 ... to the power of negative 0.7, etc., etc. Now, the amazing thing is this, the gradient right here, the gradient is, let's have a look. I'll move back to a equals 1. And let's have a look at the values here. F of a, that's the value of f of a, 2.718281, blah, 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 blah. That's e, okay, because a equals 1. So it's e to the 1. But look at the derivative. The derivative is exactly the same value, 2.71828, blah, 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 blah. And as I move a, can you see that f of a and f dash of a are in fact the same value? In other words, the derivative or the gradient at that point is the same value as the point itself. Isn't that amazing? And what that means in terms of our derivatives then is that f of x and f dash of x are exactly the same value, and that is e to the x. So that's a very special property. It only occurs at e. It doesn't occur at 2 to the x or 3 to the x or whatever else. It only occurs at e. E has a direct one-to-one proportionality with its value of f of x with its derivative. Now, would you like to know why? If you do, great, but I'm not going to tell you in this video. In this video, we're just going to have a look at what that means in terms of finding the derivative of equations with e in it. If you would like to know why it all works out, then on your learning schedule, there is an optional second video. It's about 13 minutes long, not done by me, and it will attempt to explain to you why this sort of one-to-one proportionality exists with e to the x. We're just going to concentrate on a whole bunch of examples. F dash of x is equal to e to the x if f of x equals e to the x. There you go. Nice and simple. Let's have a look at a whole bunch of examples and see how that works out. So if y equals 2 to e to the x plus 1, then dy by dx is equal to, so the 2 remains constant, and e to the x is e to the x, so it's 2e to the x, and the 1 drops off the radar. So dy by dx equals 2e to the power of x. Example 2, y equals e to the 2x. Now already we're getting into territory where we're going to have to use the chain rule. So the chain rule, remember, is inside out. So the inside function is 2 to the x, and the outside function is e2 to the x. Sorry, e to the 2x, beg your pardon. So if I work out the derivative, then I get dy by dx is equal to, so work out the derivative of the inside, that's 2x, and the derivative of 2x is 2. And then I work out the derivative of the whole function, which is e to the, and that's e to the. So it's 2e to the 2x, and we're done there. The next one, y equals 1 on e to the x. Well, we're going to do a bit of manipulation first because we want it to be e to the power of, not 1 on e to the power of. But we can use our exponent law that 1 on a to the n is equal to a to the negative n to make this equal to e to the negative x. And now we can work out the derivative. dy by dx is equal to, find the derivative of the inside function, that's negative x, and that would be -1, and then find the derivative of the entire function, which is e to the, and so that would be e to the negative x. So it's negative e to the negative x, or if you want to, you can put it back into positive exponents there, -1 on e to the x. That's that done. Feel free to pause this video and see if you can work ahead to work out each of these problems before I get to them, and then you can use the video to check. F of x equals that expression there. We're just going to use a combination of change rule and sum of derivatives in order to solve this. So the first part is e to the x squared plus 1. So I find the derivative of x squared plus 1 first. That's 2x. And then I multiply it by e to the x squared plus 1 because that's the derivative of e. Then I've got x squared, so that becomes 2x, and the 1 disappears. So that's what f dash of x equals. Example 5 is we can't touch this until we just have a sum or difference of functions, if you like, involving e in this case. So I'm going to split it, 3 to the e x squared over e to the 2x plus e to the x over e to the 2x. That's equal to 3 e to the x squared minus 2x plus e to the x minus 2x is negative x. So there's my single line of expression there. So then I can go f dash of x, which is equal to, again, inside out, the inside function is x squared minus 2x. So the derivative of that is, 2x minus 2 e to the x squared minus 2x, because the derivative of e is e, and we then have the derivative of the inside function negative x, which is minus 1. So we're going to have minus e to the negative x like so. And that's done. We could do a little bit of tidying up. We could maybe take out a common factor of e to the x and all that kind of stuff, but I think I'll just leave it at that for this problem. Y equals the square root of e to the 2x plus 1. That's fine. We've got a few functions here. We've got the very inner function, which is 2x. And then we've got e to the 2x plus 1. And then finally, we've got the square root function there. So we work out the inside function, which is 2x. Whoops. Like so. So, oh man, sorry. So e to the 2x is, the derivative of e to the 2x is 2e to the 2x, like so. So the derivative of the inside is 2, and then we've got the derivative of e to the 2x, which is e to the 2x, and we've got the plus 1, which is just nothing, so we're left with 2e to the 2x. The next function we've got is the square root, which is to the power of a half, if you remember. So I bring down a half like so, and I've got e to the 2x plus 1 to the minus a half, because a half minus 1 is minus a half. And tidying up, we've got e to the 2x outside of e to the 2x plus 1 to the power of minus a half. Or if we want to tidy up a little bit more, we can say that's e to the 2x all over the square root of e to the 2x plus 1. And then we're done. Okay, example 7 just has one extra step in it, which it says find the gradient at x equals 2. So first of all, we work out f dash of x. So f dash of x is equal to, just realized over here I didn't put the y by dx in my excitement. Okay, f dash of x is equal to, so x squared, derivative of x squared is 2x, and then the derivative of e is e, so it's e to the x squared. And then the plus 1 disappears. So the derivative is that. And it says to find the gradient at x equals 2. So f dash of 2 is going to be 2 multiplied by 2 multiply e to the power of 2 squared, which is equal to 4e to the power of 4. And that's all we need to write. That's the exact value of the gradient at x equals 2. If I type that into my calculator and get an approximation, it will be just that, an approximation. One more example, it's outside the course, but I just thought I'd leave it in there as an example of where we can go. Well, how do we work out f of x equals 2 to the x? The derivative is not 2 to the x, but what we can do is a little bit of trickery here. We can say that 2 is equal to e log base e of 2. That's just by definition of how that works. okay, which is just e to the ln of 2. Okay, so that means that f of x equals 2 to the power of x can be written as e to the power of ln of 2, which is just a number, multiplied by x, which means that the derivative is, work out the derivative of the inside, and the inside is just a number. It looks fancy, but it's not. It's just a number, ln 2x. So derivative of that is just ln of 2. And then we have e to the ln of 2x. And then working backwards again now, I can say that's ln of 2 multiplied by 2 to the power of x. So that is how we would find the derivative of a base that's not equal to e. And it sort of helps explain why e is such a powerful number to utilize in calculus, because we can express any base as a base of e, and because of the particular nature of e having its derivative as being itself, we can effectively find the derivative and hence the gradient of any base raised to a power.